we want to determine the domain of this function. Now the domain, this is a collection of all numbers that make this expression computable. So when I do these problems, I think, what numbers, if any, will make this non-computable? So we know we got a fraction, so just look in the denominator. We don't want denominators to be 0, so what's going to make the denominator 0? So I'm thinking, I don't necessarily have to write this every time, but 5 minus x, what's going to make that 0? So if I add x to each side, I'll get 5, right? So here's the domain. It's all numbers x except 5. Now the way they want us to write this is an interval notation. So in interval notation, here's what I would have. If I drew the interval, and here's 5, I have to keep 5 out of here. I could have all numbers over here, all numbers over here. So in interval notation, I'm going to go from negative infinity to 5, but not include 5, so open parentheses, or, there's that union sign for an or, and then from 5 all the way to positive infinity. There's our domain. So we're looking for the domain of this function right here, and notice that it's a fraction, so we don't want the denominator to be 0, so we're just going to set this denominator 0, x squared plus 3x minus 28 equals 0. What's going to make it 0? Well, it's quadratic, so let's factor it if we can. So we'll get x and x. Now, what are the factors of 28 that will give us a 3? Well, what we can use? We can use, how do you get a 28? 28 and 1. Well, all right, so 28 is equal to that. We can't get a 3 out of that if I add or subtract. Now cut in half and double. 14 and 2. If I add or subtract, I can't get a 3 out of that. Cut in half and double again. 7 and 4. There we go. Those differ by 3. So let's use 7 and 4. Now, that 28 is negative, so that's a negative sign. That means that these two numbers have to have opposite signs. Now, I'll put the plus sign with the bigger product. Now, the way I wrote it, the 7x, the inner product, is bigger than the outer product, 4x. So I'm going to put that plus sign with the 7. So I'll have x plus 7, x minus 4. And now I can see that x could equal negative 7 or 4. Now, that's going to make that 0. So I want to exclude those. So we're going to exclude these. All right, so I'll write the domain here. So, just draw a picture if you're not sure how to write it. I'm going to exclude negative 7, and I'm going to exclude 4. So I want these numbers, and these numbers. So what do we have here? This will go negative infinity to negative 7, open, because we're not going to include that 7, or right in the middle, negative 7 to 4, close, open parentheses, right, because we don't want the 4, or from 4 out to infinity. There's our domain. Pick any number in that collection and put it into this expression. It will be computable. We've got a rational function, and we want to know one of three things here. Part A, the function has one vertical asymptote, or B, the left vertical asymptote is this number, and the rightmost vertical asymptote is this number, so they're saying there's 2, and C, there's no vertical asymptotes. Well, vertical asymptotes are going to come from where a denominator is 0, so let's take a look at this function and see if we can reduce it. Let's try to get it in simplest form. So let's write the function and then see if we can determine what's going to make that denominator 0. So I'll have x cubed over. Now this is 8x cubed minus x squared minus 9x. Now let's see, there's an x common, so we can take that x out. So we will get x cubed over, now take that x out. In doing so, we're left with 8x squared minus x minus 9. Now, let's see if we can factor that to see what's going to make this thing 0. So we'll have g of x equals x cubed over x. Now, we've got this 8 and a 9. Because they're so close together, I think I'm going to try an 8 here. and a 9 here. So I'm going to try this. 8x and an x, and then I think I'll put a 9 and a 1 because I'm thinking this is going to give me 8x and 9x. I can get a 1 out of there. The 9's negative, so they're going to have opposite signs. I'll put that negative sign with the larger product, and the way I've written it up here, the inner product, 9x, is bigger than the outer product, 8x. So I'll put the minus sign there. A minus, plus. Right? Now I can see from the denominator what's going to make it 0. Well, 0, oh, you know what? Before we do that, I can simplify a little bit more, right? I can factor this x. That x will go with one of these, leaving an x squared in the top. So here's our function when it's reduced. Our function reduced is x squared over 8x minus 9, x plus 1. So from the denominator, we'll get x equals 9 over 8 and negative 1. Right? So we have to exclude these values. So these are going to be our asymptotes. So on the number line, this is left, right? This one here is on the left, and this one here is on the right. So I'm going to choose up here at the top in our questions, I'm going to choose B. And I'm going to say that the leftmost asymptote is negative 1, and the rightmost asymptote is 9/8. What we want to do now is to find, that means construct, a rational function that satisfies these conditions. We've got vertical asymptotes at these two numbers, a horizontal asymptote at this number, and an x-intercept at this number. Well, let's see if we can build this function. Let's start here with these vertical asymptotes. Now, I know vertical asymptotes come from denominators being 0. So here's what we have. We have negative 3 giving us a 0, and 5 giving us a 0. So we could construct this. Those numbers are going to give us 0. So how about x plus 3, x minus 5, right? Because we want these to be 0. So what's going to make this thing 0? The opposite signs. So plus 3, plus 3 here, opposite sign, opposite sign. Now if I multiply that out, I'll get x squared minus 2x minus 15. So this function here, this rational function, now it's given that t has to be greater than or equal to 15. All right, so this rational function where t is greater than 15 gives the body concentration in parts per million of a certain dosage of medication after time t. So n is the dosage and t is the time. So the dosage depends on time. So I'm going to write that here. So dosage, n of t, dosage depends on time. And that time is going to be in hours, all right? So dosage is in parts per million, time is in hours. Now here's part A. Find the horizontal asymptote of the graph and complete the following statement. So horizontal asymptote, this is a line that the curve approaches but never touches. Now it's a horizontal line. So look at the graph here. Here's this graph. It looks to me like it's coming down, down, down. It looks like it's approaching this line right here, which is 0, right? N would be 0. It looks like it's approaching that, and so if it keeps on going, it's going to get closer and closer, but never touch it. So I'm going to say this, as over here now, as n of t approaches, n of t approaches what? As t approaches infinity, here's time. This is time. As the time goes out to infinity, right, if you just keep going out and out, n of t, right, as time gets more and more and more, as more time goes by, what happens to the concentration? Well, it looks like it's going down, down, down to 0. So I'm going to say this. I'm going to say, as n approaches, well, n of t approaches what? 0 as t approaches infinity. And that makes sense. If you take some kind of medication, as time goes by, the concentration, it metabolizes out of your body, so the concentration comes to 0. So I'll write what I just said here. As I look at the graph, I can see as time goes by, the concentration of this medication gets smaller and smaller and smaller, and eventually it just goes to 0.